Keeping a volatile, continuous-time stochastic system alive requires confining its state within a defined, safe operational boundary. We represent the underlying motion as an Ito diffusion, where the system is subjected to constant, random perturbations that drive its trajectory over time. In this model, the boundary is a terminal threshold. Any trajectory that crosses the edge is permanently removed from the system. It is effectively killed. This creates a specific mathematical challenge. Because trajectories die at the edge, the process is sub-Markovian. Probability mass is constantly leaking out of the region. Defining the information-theoretic cost of survival is difficult in this state, because standard entropy measures rely on a stable, mass-preserving probability distribution that doesn't exist here. To quantify the uncertainty of a dynamical system, we typically look to the Ruel-Pessin entropy identity. The formula is mathematically incompatible with survival condition diffusions because it strictly requires a system that preserves its total mass over time. Historically, researchers attempted to resolve this by adding the domain's escape rate directly into the dynamical entropy budget to force the equations to balance. This creates a structural mismatch. Dynamical entropy tracks the growth of uncertainty inside the system, while the escape rate measures the loss of trajectories at the boundary. The elliptic stage zero theorem package was developed to resolve this conflict by separating these physical properties. The objective is to reconstruct the mathematics of the process so that we can stop the mass leak while leaving the internal dynamics of the system intact. The stage zero package is organized into 4 distinct modules: constructing a conservative Q process, analyzing endpoint control, establishing Pessin closure, and identifying the correct pressure placement. In the first module, we shift our focus from the leaking process to the system's principal eigentribble. We apply a Doob transform. By using the principal eigenfunction to reweight the trajectories, we stop the loss of mass and create a closed vector field. This transformation produces the Q process, a conservative, mass-preserving dynamical system. Analyzing this process requires distinguishing the endpoint quasi-stationary distribution from the quasi-ergodic measure. The quasi-ergodic measure is the time-averaged occupation law of the process, specifically for trajectories that have survived. This specific measure provides the stable foundation necessary to support a stationary entropy theory. In modules 2 and 3, we can now apply tools designed for stationary systems to this conservative Q process. With the mass leak stabilized, the system admits a random Pessin identity and an Ozolets theorem. Module 2 focuses on endpoint control, examining the Radon-Nikodym term that compares the conservative process to the original killed dynamics. The mathematics show that this Radon-Nikodym term is strictly sublinear. Because it is sublinear, any distortions occurring at the boundary vanish when we take the long-term average. This isolation allows the true dynamical entropy of the system to be measured independently of the boundary effects. Module 4 addresses the correct placement of the escape rate. The escape rate belongs within the Donsker-Varadin pressure balance, rather than the entropy budget. The escape rate is identified as a free energy value, determined by the mechanism of soft killing or Dirichlet absorption. While the entropy and free energy balances both utilize the quasi-ergodic measure, they remain mathematically separate. Terms do not transfer between these two balances. This decoupling allows the dynamical entropy equations to be analyzed independently of the system's survival boundary. This ergodic framework provides the necessary basis for solving applied problems in continuous time stochastic control, where instant reaction is critical. Classical control limits were built on the assumption of a separated communication channel between a sensor and a controller. In modern autonomous systems, the architecture follows an internal loop, where the controller is integrated directly into the system. The controller in an internal loop observes the state through its own causal history, without an external communication link. The primary operational limit in this setting is the irreversibility of the control commitment. Because the system sits in an internal loop, we need a new mathematical framework that measures the information cost of these commitments without relying on channel capacity. The city bound addresses this using Massey's directed information. The continuous time city identity quantifies exactly how much entropy a controller removes. The identity relies on a strict causal history convention. Conditioning only on the information available at the time of each decision ensures that we do not include retrospective data from the future. This connects the applied control to the Q process entropy, which represents the uncertainty injected into the system at each step. To maintain survival, the controller's directed information rate must compensate for this injected uncertainty. To prevent the system from exiting the safe boundary, the directed information rate must exceed the Q process entropy. Spectral exit scales and thermodynamic limits imply that this survival can only be maintained over a finite time horizon.